So guys, I'm Zain Nasser. As you can see, I'm the author of Machine Learning for Civil and Environmental Engineers. I like to call it MLC. And I'm going to be hosting a few recordings, a series of recordings actually. And I'm really trying to cover the different chapters, different ideas that mainly revolve about machine learning, how we can use it as civil environmental engineers, why do we need to learn it, how is it important, how can we leverage it for our cases and our area and domain. And by doing so, I'm hoping that hopefully it becomes, machine learning in general becomes something that we can all, work on, rely on. I don't want to use the term modernize, but maybe advance our engineering profession a little bit. And just like everything, in life, we have different views into things, and this is one way to look at machine learning. One textbook. There are multiple ways, multiple textbooks, multiple resources. So my advice is always to try to learn and read as much as you can. Collect ideas and go through different articles, different sources. And of course, I have my two pets around. So if you hear somebody fluffing, that's probably them. The way I would like to structure these recordings is I'm trying to keep it simple. So I would like to have the slides on this side and also bring in the PDF on the other side. And between both, hopefully we'll get to, a smooth sail between the different topics and ideas. I'm very, very aware of how my PPT looks like. I like this view. I don't like when they have like a full scale mode. I like to see the slides on the side, so I'm hoping this would be okay with you. As you can see, we're gonna start with, let's say, recording one. And the goal is very simple. The goal is actually very, very simple. I'm hoping this would be as simple as I'm imagining it. So if you would like to read something, the first thing is to look for the title. So in our case, we have a title, and our title is Machine Learning for Civil and Environmental Engineers, a practical approach to data-driven analysis, explainability, and causality. So as you can see, we have a few key terms. So the overall theme for this book is really machine learning. So machine learning as a science, as a philosophy, as a tool. And we're going to be using these principles, and we're going to be focusing on what civil and environmental engineers do. So this is where the second term is. Now, some of the terms I'm going to be saying now might be a little bit abstract, but hopefully as we go through the different recordings, they become a little bit easier to visualize. I'm sorry. Everything is going to start to buzz now. So let me pause this for a second. I'll be back. There we go. I'm sorry about that. So I was saying the third item would be data-driven analysis. So this is something good. As whenever there is machine learning, there's a very good chance we're going to see data. And whenever we have data, well, the goal has become, well, how do we create models? How do we explain these models? And in the very, very good chance, we might even be able to figure out new things about these models. This is where causality comes into play. Well, first recording. So hello, friend. If you're familiar with Mr. Robot, this is actually episode 1. This is how the show starts. And this course outline should be something we're gonna follow this as close as possible. So we're gonna have a preface, and then we're gonna have educational themes, data, different algorithms, fitness indicators, then coding-based, coding-free chapter. Then we'll go to explainability, we'll go to causal discovery and causal inference. These will be 2 heavy chapters. And hopefully we will end up with advanced topics and some recommendations. And to start, so basically, if you're a student, this would be a very, very good chance where you stop the record, you stop watching this recording, and you jump into the next chapter, to the next recording. If you happen to be a faculty member or like a professor instructor, I would advise you to stay a little bit and maybe hear a few thoughts or ideas about these 2 items here, the preface, as well as the educational themes and methods. If you would like to still just watch the following, that'll be great. It's just I think the next material is not really uh, may not be as important for students as somebody might think. However, I do think that if you happen to be a grad student or like maybe doing some research and stuff, some of the ideas and thoughts might help you a little bit. If, for instance, you're one of my students taking my class, whatever is going to come next within this recording is not going to be something that you would see in an exam. Um, it would be something that somebody might think about when they create a topic or a material or a course basically. So this is why I'm just having this disclaimer. If you don't want to continue watching, that'll be fine because you're not really missing on a lot of content that you would see like in a homework or an exam. So let's jump ships. Let's go to the PDF, and I have it highlighted even. So this is the preface, and um, the way the I've tried many ways to structure this book, and I found out, or I think what really worked out for me is the following. We're gonna have a chapter, and then we're gonna have a little abstract, and then we're gonna have different topics, and this is how the headings work out. So for the preface, you'll always see a quote. You'll always see something from a movie, from a TV show, from a book. And I'm trying my best to keep it this a little bit lighthearted, because I know sometimes a new topic all of a sudden might be something not that that friendly. But let's see. So in this case, in this recording, the preface is really trying to share a few thoughts of what I had in mind while I was doing this book. And I think it's important to share because the experience was interesting. It was a little bit eye-opening. I didn't think it was going to be this smooth. But I also had many questions, and I wasn't really sure if the answers I had or the methods I followed addressed them properly or not, or like even in a way that I was happy about. But eventually, I think whatever I have put down together more or less conveyed everything I had in mind for this for this material. But I also am thinking that some of you might also have like different questions or even the same questions, and perhaps if you just hear somebody sharing their experiences, it might help you a little bit. So if you think this is helpful or like you have like some things to add up, please reach out to me. I'm very easy to find, and it would be interesting to hear your thoughts. So the big idea or the continued theme across the different recordings will be the following. Very simple. We always try to simplify things. We're civil environmental engineers. We have problems. We have a lot of things that we have to deal with. And the theme is the following. Can we use machine learning to help us with these things, with these problems, with these phenomena? And if we do, well, great. Then what are some of the ways that could help us? And whenever you see this, you're going to have to really take a step back and try to think of the following. When you use a tool, you're basically trying to say, well, I have this tool and I'm trying to apply it to solve something. Another way to think of the almost similar approach is you have a tool and you try to create solutions. So there are two different things, actually more than two, but for the sake of discussion, let's think about two things. Apply to solve or create solutions. So this is really the big idea behind this preface, and I would like to always, I'm really doing my best. I'm trying to be very clear with the expectations because I know sometimes that we always have, our own, uh, ideas and the way we perceive things. But for this book, I'm really trying to not be as technical as possible. I love technical books. The first few drafts were very technical, to be honest. However, after I've read them a few times, it just seemed too dry, uh, too mathematical in a way, too cookie cutters, and yeah, I guess. So I took a step back and I was like, okay, let's keep this a little bit different. Let's still keep the technical format, the technicality in it, but let's just deliver it in a much smoother way. And I know I'm taking a big risk on this, but hopefully it will pan out. So the way that my experience started with ML is the following. We always, you have like a phone update, IO update, and then you can say, oh, well, they changed the algorithm. You know what? It's now it doesn't look good, or it's not as fast, or it's showing me all these different things. So in a way, we really know, or we interact with machine learning a lot, but we don't really know like the ins and outs of it, if this makes any sense. So we know we have in a software, we know we have like those apps on the phone, we know how they work, but the backside of the story is the one we don't really know as much. And because of that, uh, we have to have, or teaching machine learning becomes a little bit of a challenge because a lot of things, as you would see, the audience is, you're right for your audience. The audience is somebody who know about machine learning, but they don't really know how, like how does it really work out. So it's always going to be a challenge. And because of this, you'll see in my writing, I'll always try to be like, sometimes very technical, sometimes I back down a little bit because I feel that each context refers to different things. You'll also find a lot of footnotes. And these footnotes are something that I really like. At one point, they were to be endpoints, so that you find them all the way at the end of the chapter. But then footnotes was the thing that I went for because I think whenever you have like a thought, you go down there and it explains why is it there. So I find that to be something interesting. I like it. Um, Sometimes you'll also see me asking questions and trying to answer them. These are the questions I really had in mind while, whether like writing or during I'm doing like a research project with my students or for somebody like for some grants and stuff. And these questions come and I always wrote them down. And I think having these questions help a little bit because if I had them, that means other people would have them too, and it might be something interesting. You'll see that there's going to be a little bit of some discussions, very short storylines or stories that I've experienced, and I think these are interesting because they relate to the chapters very well. At the end of the day, you'll also find me saying that, and this is where other professors, faculty members, instructors, teachers, engineers may agree or disagree with this. When you try to teach something, you have to take some leap of faith of deciding which way you want to go for, or like different ways. But I think one of the things that helped me a lot was uh, the following. If you learn machine learning as a methodology and a philosophy, it becomes you gain a little bit more than learning it as an applied science. So if you learn machine learning as a methodology, as something that would help you create solutions, or as a philosophy, something that would help you change the way you think a little bit about your problems, it becomes a little bit easier to generalize and know the negatives and positives. I feel much more than if it was taught as an applied science. Because if it's an applied science, a lot of the negatives I think in my mind is when you go for an applied science, you're basically telling the learner that this is how you do it, I guess. Or this is the only way, or one of the only way to do something. So that the creative portion is a little bit off, but it really depends on the faculty. In my case, I like the more methodology philosophy kind of an approach. So to start, as you can see, I'm MZ Nasser. MZ stands for Mohammed Ziad. These are two N's, not M's. And this is why we have this underline there. So I got my PhD from Michigan State. I'm now at Clemson. This is 2023. So hopefully this will put things into perspective. A lot of the writings they have are actually influenced by many, many other writers, professors, for instance, Professor Nick Huntington has a great book on causality, the effect. Judah Bird as well, and many other writers too. So this is why you would see the difference between full engineer technical writing slash a little bit of philosophy, because I was influenced by the writings a lot. I'm fortunate enough to be on different committees, chair of different committees, and the domain has been very kind to me, and I'm thankful for them because they accepted kind of AI stuff. There are many groups that are doing AI machine learning at the moment, and they're doing a great job. And hopefully we'll all get to work with each other and do good things. So learn more about your audience. This is a very good advice. What I also like to mention here, and I find this is why I said if you're a student, you might want to watch this. So I didn't really do well in undergrad. I think my GPA was 2.2 at some point. I graduated with 2.6. I think I had a few semesters where my GPA was like 1 point something. So it wasn't a smooth experience, but then you graduate, you get to do research, somebody believes in you, they help you, and you continue. And this is why I usually start my courses with this paragraph, because I want the students to know, it's GPAs are great, degrees are great as well, but it's not something that you should, it should uh, identify with. It's just one thing out of many, many other things that you could do. So I'm really hoping. I know when I say this, I'm usually a little bit afraid that it would be taken negatively, but I'm hoping that this would help, a little bit in with different students. There is a very big list of people I'm gonna be thanking, and I don't want to forget anybody. But as you go through the book, you'll probably see those names, and I'm thankful for all of them, because at some point here and there we've interacted. We have like research or like professors or teachers, and it's great. It's great to have a very supportive community. It's actually very, very helpful. It makes our life easier. So moving on. So the way I got into machine learning is the following, and I think this is important to know, because we all get exposed to things in different parts, and each little part tends to build up other things. So I was working on a problem. I'm trying to figure out fire resistance for RC columns, and we've tried a few things from building codes, a few empirical methods, a few theoretical methods, and the error range is usually high. And then we started machine learning, and we found that the error was actually very, very small. So the first question that was in mind is the following. If this machine learning model was able to predict fire resistance with with high accuracy that exceeds at that point everything we had in building codes and equations and all those things, then if I know how machine learning was able to predict the phenomena, I will be able to reverse engineer that, and then I will be able to figure out what the phenomena is. How can I, predict it very easily with high accuracy? So the questions I had were really two: how machine learning works, and why does it work so well? And if you know the how and why, this is actually very good, because then you can come up with new methods, new theories. It will help out a lot. Uh, so from there, well, to know how is actually simple. How machine learning predict with high accuracy. It's simple because machine learning models are non-parametric, which means, as you will see in chapter 2, uh, they don't have to follow a specific equation to solve something, to predict something. They figure out things within the data. This is like a very rough abstract of how things work out. Because they're non-parametric, then they don't have to be parametric, and hence they can connect things much, much easier. This is how. Why isn't easy to know. Why is actually why we have multiple chapters on why. However, if we know why they predict things with high accuracy, things becomes a little bit interesting, because this is where you're going to go back and see, oh, okay, now I see why, and this is how I'm going to be able to predict this item or this phenomena or this effect very easily next. So this is the introduction. I mean, how my introduction was. So the book is actually, as you know, just like every other book, we have different chapters. And each chapter hopefully will figure out something about a specific sub-area within machine learning. We start with general ideas and then we go for more in-depth ideas. So chapter 1 is surprisingly how to teach, or some of the approaches or pathways to teaching machine learning. And then we go to a little bit of history, different algorithms. Then chapter 3 is all about data and statistics. It's like a mini review slash things that you need to know before you use machine learning. Chapter 4 talks about specific algorithms. I think we're about 30 or 40 algorithms we're going to be discovering. A lot of things in chapter 4 are really visual because I happen to be a very visual learning, and for me to visualize how things work out, I would like to see them, and you're going to see a lot of emphasis on visualization. Then chapter 5, we're going to be talking a little bit about how if you have a model, well, how do we know if this model is accurate or not? So what's the performance of this model? 6 is when we get to practice ML. So we're going to have to go through a number of tutorials, case studies. We have data sets and codes online, so you can download these. You don't really have to buy the book. All the lecture notes as well as the data sets and codes are free. You can just go them, get them from there and start with them. Chapter 6 is where we practice. Chapter 7 is where things start to be a little bit more technical, where we go after explainability. So we're going to have to cover what explainable machine learning is, interpretive machine learning is. Chapter is about causality. Chapter 9 is one of my favorite chapters. It covers advanced topics, which is basically different ideas and themes within machine learning. That goes a little bit beyond what I don't want to say need, but we might think we need in civil environmental engineering. Chapter 10 is where we end. So we're going to have recommendations, suggestions, best practices. I think these are great. As you can see here, you can find all the lecture notes from my website or even Wiley's website. You can just click on the link and download them from there, practice them. If you have any questions, send me emails. I would love to hear about those. We also have an appendix. The appendix is actually very large and we weren't able to print it, so it's online, and you can also visualize it from the previous link. If you happen to see some of the chapters, they have this little snowflake, and the snowflake is actually a star, and the star is if you really zoom in, I believe, I think this is, yes, so this is the one that we're looking for, and this is because a few chapters were actually written in Michigan, and it's cold, so I have it from there. Things I would like you to try. So there's machine learning is a little bit interesting because it's very, very fast. And I mean advancements. It's like every other hour there's a new algorithm or there's a new paper or there's a new technique that's out. So you don't really I don't think it's a good idea to start with something very complex. I think it's always easier to start with simple stuff and then go through so general to in-depth. But if you happen to have time, there is a lot of good things that go over Twitter or LinkedIn. A lot of, researchers, coders are there, so they share a lot of news, digestible news. Coding is interesting, or programming is interesting. You'll see that I don't focus much on programming, actually. I think this book might not be the best book to learn programming. There are many, many other books which I cite in this chapter. We'll see later on, that are very, very good at teaching programming. I think what my vision was, or what I feel we need as engineers, is we need to learn machine learning as a philosophy, as a methodology, rather than a programming. Because if we focus on the methodology part, things become very easy and program becomes like a skill that you can do. So if I have some programming stuff in the next chapter, but in the data chapter, but it's not something that I'm focusing on. However, we're going to be focusing a lot on machine learning through software, which we will see soon. So we're gonna have softwares that run the machine learning for us. And to learn these, you want to know the principles. What are here? So of course, thank you to all the great people that I have met, my students, Clemson, Wiley, my family too. Everything was great. Their support was immense, and I'm really hoping that uh, this is something that you look back and say, oh, you know what? I know this guy, and he was, bothered me a lot, but and thankfully, this material turns out helpful for everybody. I'm really hoping so. Um, let's see. So now we're gonna be moving to chapter 1, test teaching methods. So teaching is actually something very, very interesting because there is a big component to deciding things, picking and choosing how you want to teach something, especially if you're like me, like a junior faculty member, or like somebody who's an assistant professor. Usually senior professors are much better than teacher than they have experience. They have a lot of experience. They have seen a lot of students' cases, so they tend to be much more knowledgeable about this, in general. And if you happen to be like, if your department or your school have, one of those, you know, education experts, my advice is talk to them, learn from them the, top 5 things or top 10 things that they'll be able to share with you because it helps a lot. And when you write something like this, it becomes a little bit difficult because each of us learn things, like in our own, like for instance, I'm a very visual learner, so I have to see things. Other readers may not be. And this is where, if we write, we usually write because like we write because of our points of view and stuff, but the reader is unfortunately they have to follow what we write. They don't get much say. And hence, my decision to go between, technical and a little bit on the soft side with writing, because I think it just generalizes the material a little bit. It makes it easier for everybody to see. However, in general, at least, throughout my school, my teaching and stuff, I really think that a lot of engineers are active learners. There's a very big literature on education for engineers, and these are only 3 citations, but there is hundreds and thousands of citations. And being active learner means you want to see things, you want to experiment with things, you want to see demonstrations, you want to go to the lab and do things. And because of this, it actually translates very, very well in engineering. And if you really think about like our methods, like if you open a building code, we have methodologies, we have systematic systems, systematic methodologies. We have first principles, and we have equation 1, 2, 3, 4, step 1, 2, 3, 4, and so on. And this is how we go from A to Z. We have principles, and we have things set in order, and most importantly, in a logical way. So for instance, you can calculate capacity before finding out, what, for instance, A or C is in RC design, or what the yield strength for the material for seal design and stuff. So first principles, logic, all of these things makes our life a little bit easy. And if you know my advisor, Professor Kadur, I was a student for many, many years at Michigan State. He always say, writing is like a plot in a movie. You have to you have to follow them to make it interesting. Same thing with our principles. You have to know why and how before you jump into the math, right? So this is how things work out. And if we go to the next page, we have this very, very famous equation. So if you're trying to find the moment capacity, let's say in a W-shaped steel section, it's really simple. Moment is M, it's resistance and bending, so how things bend. And we have 2 parameters, Z and Fy. So Z is the plastic modulus, it's a geometric property. Fy is the yield strength of steel grade, of the grade of steel. So it's a material property. And between them, as we multiply, we get the moment capacity. Very simple. However, what we don't really notice much, or we don't talk about much, is the following. 1.1, this is an equation, and we're all familiar with equations. But if you really think about what an equation is, it's something very beautiful. It's a representation that's visual. So you can actually see, you see m, you see z, you see times, you see fy. You can visually see the parameter. This visualization expresses the relationship between the parameters. The moment is a function of the multiplication of the geometry z and material property fy. And because it's a multiplication, implicitly, we're going to say the following. Well, this is why m is this much, because it's a causal effect. Z is this much and fy is this much, and we multiply them. Now, once you start break things like this, you're gonna start saying, well, okay, this is good. How can I do the same thing for machine learning? It's gonna be hard, but we'll get there. We'll get there. So equations are something that most engineers are familiar with, and it's something that we can visualize easily. We know the parameters, we know why it's there. And when we learn engineering, it's usually the same philosophy. Here it is. This is how it's look like. This is the relationship. This is how you substitute to get your outcome. This is moment capacity. Now, if we think about the collapse of a building or about something much more complex, I don't know, soil erosion in a coastal area. Well, the phenomena is complex. And let's say if we're talking about collapse, we don't really have an equation that tells us if you plug in A, B, and C, this is how the building collapsed, right? There is many parameters, many parameters. The relationship between the parameters is not as easy as multiplication. It's likely to be highly nonlinear. We don't even know what the form is. That's discussion for a different day. But complex phenomena is sometimes associated with complex representations. Simple phenomena, simple representation. If you also think about finite elements, so I actually started as a finite element modeler with my master's and PhD. But finite element simulation is something like an equation. You have like this software, you plug in some information, it does the math, it gives us an output. The difference between software, between finite element and machine learning is we know how the finite element works. We know how to discretize the elements, give them degrees of freedom, matrices, multiplications, solve it. Machine learning is not that easy. So the physics component is actually not there, which is highly interesting. So because we have these differences in the methodologies themselves, when we start to think about teaching machine learning, well, we're going to have to ask yourself, well, how do we teach finite element? How do we teach section analysis? How do we teach RC design? The way that you're going to teach machine learning, it has to not mimic it, but it has to have those essential principles in there too. Otherwise, there's a very good chance we're gonna lose the audience, right? They're not familiar with this. They need to know why we're doing this. So machine learning as an education material is basically going to come down to the following. When you think about education, you always think about learning objectives. What are the objectives of this material, this course, this textbook, these lectures? And in my head, I really had three. And I apologize for saying me. It's I think it's just the way I related that to the textbook, and I'm not really trying to gain a lot of it a lot from it. It's just a little bit easier to say. So basically, we have machines. So we need to introduce the principles of machine learning. We need to see what these are, how they are, and how do those align or contrast what we normally do. Once we learn the principles, we have to apply them. So we have to show case studies, we have to practice, we have to train, we have to visualize. And eventually, we would like to have a platform or like a way for students and engineers to collaborate, work together, and take whatever we have these principles and start to build cool solutions, cool methods, cool algorithms. And this is where we start to think about coding. And as I mentioned earlier, coding is I view it as a skill. It's you need to know how the syntax work out together and stuff. But before that, you really need to know the field, like why are we doing this? For instance, what is machine learning? How does it help us? Before we go and jump into coding, I don't think it's I don't think learning ML as a mathematical exercise is what I would like to do. I mean, personally, I think. I think learning how and why, then what is it, and then we can take all those information, those ideas, and just try to put them. Okay, well, to get this, I have to teach the algorithm or the script, but this is what I would like to do. ASC Exceed was actually very, very helpful. If you're a faculty member, Google this, try to attend it. I had great mentors, David and Fitty. They were brilliant. They helped me a lot. It's interesting. So if you're thinking about programming or coding, I always use this in my discussions. I don't really think that we should all be machine learners or like expert in machine learning. Just like I don't think all of us need to be like FE experts or modelers. We just need, many of us need to know what it is, how to use it. Just like many of us know how to use, FE or softwares or you know, a lot of the other things that we know. I'm trying to avoid saying a few examples because I don't think that they're going to be the greatest thing to mention now, and this is why I'm pausing a little bit. But when it comes to teaching, well, there are multiple ways. So there are multiple ways to teaching, and it took me a while to think of these, but actually there's many more other ways in publications that could work out. But the easiest thing is the following: if you're thinking about teaching something or learning something, you take a course, right? So the simplest form. So if you're a faculty member, you create a course. And when you create a course, at least in my mind, this was the flow. I need to create a course. Well, okay, what am I going to do? Am I going to teach ML by programming or am I going to teach ML by application? And I was in between the two. Usually, if you're like in the where I'm at the moment, uh, Europe, US, Australia, maybe a little bit. Civil engineers, we don't really have a lot of programming courses. But they may have a course or two in their sophomore or freshman years just to do something with program. But machine learning is a course that you'll teach later on, so there's gonna be a big gap between coding and stuff. This is why I was trying my best to avoid programming. And I think teaching ML by application, which is basically teaching ML by using platforms that provide coding-free ML solutions, and this is where we're gonna have to highlight this one here, like those examples, becomes actually very interesting because now at this career stage, you don't have to limit yourself to learning coding before you learn machine learning. You can learn the principles and then use the tools or these platforms to create models for you. And it should be a little better because you know the principles, you know what to expect. The coding is missing, but this is something you can always learn. And I was also thinking about, like practicing engineers or senior engineers. Sometimes it could be a little bit challenging to learn like a new language. It might be like the easiest thing, just because maybe you don't have time or you have a lot of things to worry about. So I was trying my best to come up with solutions to avoid having somebody saying, well, I can't really learn coding, or I'm just too busy to learn coding, so I don't want to bother with machine learning. So I was like, well, it's easier to learn the principles than apply solutions and stuff. There is always a very good chance when once you start to apply, you're gonna have to say, okay, well, this software, for instance, or this platform doesn't really do the thing I'm trying to do. So let me code it. So this is where you can come back and have a full circle for it. Uh, I know this might be by now we've all heard of ChatGPT, Alpha Code, Encoder. And these things now it's 2023. These things are actually very good. So imagine what they're gonna do in the next 4 or 5 years, right? Yeah, every time I think about coding, I just think of these things and I'm thinking, well, I mean, if these are really good coders now and they can code things for us, uh, then it just made it a little bit easier to transition to teaching machine learning by application versus programming. I still think coding is important, as you will see here. It's very important to learn. I just, for the sake of this item here, I was trying to avoid that because I didn't want this to be a coding book, to be honest. I want it to be about the principles and concepts and how we think. Because if you master how you think about machine learning, it becomes much easier to apply it. Of course, a lot of things happen, behind the scenes, and my students, Bashirti and Taba, were actually great in helping me with the coding throughout the book. Hopefully, they're gonna graduate soon. So keep them in mind. If you have any questions, they're very easy to find, so they're great. So this is where we have to pause for a minute, and we're gonna have to think, okay, well, this is for undergrads. If we're thinking about undergrads, well, maybe having a full course is something. I mean, where are you gonna fit it? We barely have, if you're familiar with accreditation and the other things that go with it. Curriculums can be dense. It's very hard sometimes to fit a new course. You could add an elective, but uh, it's usually hard, especially in this part of the world. I know some other schools or even countries they're much easier with adding stuff. So one of the things that somebody could experiment with, I haven't done this myself, so it's just a rough idea in a paper, bits and pieces. So like for instance, in some courses like computational methods or numerical methods, you can introduce a little bit about AI there. If you're doing a few courses where it has like a heavy math component, you can add a little bit AI there, machine learning there. So the goal is with these courses, if they're designed properly, students will start to accumulate information throughout their different years. In sophomore, a little bit, junior, a little bit, senior, a little bit. And by the time they graduate, they know a lot about machine learning. Very easy mirror is the following. We have statics, mechanics, theory of structures, design. A little bit information, a little bit more, a little bit more, a little bit more. So you accumulate information, bits and pieces. Of course, if you happen to be in an institution where coding is not a problem or a hurdle, can be that's great. Grad students, postdocs, this is where actually a lot of the faculty member can have a little bit more leeway because these you can easily add a course, an elective course there. Usually students they want to do the research so they get to learn a little bit on their own independently. Come back to you a little bit. So this is where you can also go with physics-informed ML, causal ML, more complex ML models. We will see those later on. But it's just two different, spectrums to ML. A few project ideas that you might, think about for your courses. There are, of course, many other things that somebody can think about. I teach this at Clemson, by the way. So if you're like wanna if you shoot me an email, I'll be more than happy to send you like my own slides or like my homeworks, exams and stuff. It would be great to, learn about those. Mhm. Learning as let's say, both a school sometimes can be tricky. Let's say if you've been a practicing engineer for a while, let's say 5, 6, 10, 15, 20 years, and you would like to learn about coding or machine learning. Uh, the options are a little bit different. So, and this is the case where like big ideas become important. You want to know why and how. You want to know like see how what can it do? What can machine learning do that it would make your life a little bit easier, right? So this is where you can have mocks or public seminars. Usually, if you're like an engineer, you get to attend conferences. They have seminars there. There has been a lot of conferences with AI lately. ASCE, ACI, AAWE, AIFSS. There is almost in every conference there's going to be a workshop on AI. There's a lot of podcasts too. Civil engineering podcasts, fire science shows. They're actually very great. Podcasts where they talk about machine learning. There is a lot of YouTube channels actually too. You can find these. Archive is a repository where you can access hundreds of papers on machine learning. Well, it helps. Sometimes they're extremely technical, sometimes they're good. But what I like about all these things are, like when you're just like driving to work, you can like, listen to a podcast, 30 minutes or so. I'm really hoping these videos are not very long because I'm trying to avoid having lengthy videos. I know I get to lose people by doing so. But hopefully it would be. I'm hoping they just shed a little bit of light about what's happening on the side. 1.3.4. I usually get these questions a lot. For instance, is it enough to be an applier of machine learning? Do we need our engineers to be creators of machine learning? If so, how and when? Well, being an applier, usually we start by applying something. We learn something, we apply it. Then we figure out that this something actually works very well, and whatever we learned so far or whatever tools we have so far do not solve X or Y. Then we're gonna have to go back and create or modify the solutions to create other solutions that can help us figure out X and Y. So the natural progression is we usually start as appliers, then we become creators. This is like the easiest thing to compare these questions because there's a lot of I don't want to say a lot, but earlier on, like many years ago, there is a lot of skepticism when it comes to machine learning. And one easy way to answer it is actually to think about the same question, but for something that we know. Is it enough to be an applier of FE, or do we have to be creators of FE programs? If so, how and when? Well, most of the time, if you think about it, there is a few softwares that we use. X, Y, Z. I'm trying to avoid mentioning names. And these softwares are really not done by civil engineers, by real scientists, by companies, right? We just use them. They happen to be softwares that can solve engineering problems. My hope is hopefully the more we teach AI and stuff, we get to create our own AI and machine learning solutions and softwares for our problems. That'll be great startups. So the same thing in class, for instance, if you think about FE, we really teach 1D elements. And maybe sometimes you have like a school or a department that teaches 2D elements. A lot of books teach 1 and 2D elements. Some book mention 3D elements, they show you some derivation. It is because it's complex. And once you learn 1 and 2D, well, learning 3D is natural progression. It's something that you can do. Same thing with softwares. You use element X and Y, and then you go to the help manual and you find everything about Z. Same thing with ML. You start with something simple, and then you simple algorithms, simple models, and then you go for more complex stuff. So there's going to be a lot of similarities that we have, and usually with time things calm down a little bit. So um, even if there's some inertia now to machine learning, hopefully in the future will ease in a little bit. It should. I mean, naturally, when FE started too, there was a lot of discussions there about it. So as you can see, some outlines, and I think these are, a good draft for an outline. But I also think that, we have like a very diverse population of students. So as a faculty member, I would suggest that, take think about how you could easily deliver, machine to your students. I usually teach machine. So where I'm at the moment, we have 4,000 level / 6,000 level courses. So it's a mix between undergrads and grads, the students that can take the course at the same point in time. So this is what I normally do. I usually cover, these materials, these chapters. But when it comes for, let's say, projects and stuff, I would say, undergrads, this is expectations, grads, this is the expectation for a project. If you happen to teach purely undergrad or purely grad, then maybe dividing stuff becomes a little easier. The thick lines here imply a midterm. So for instance, for undergrads, we normally have 2 midterms. So up to chapter 4, a midterm, up to chapter 7, a midterm, and then you have a final exam. Grads students usually have 1 midterm, a final, and a project, a few homeworks here and there. So this is the expectations. As you can see, chapter 1 teaching method, it would be maybe somebody can discuss it there, but I just don't see it as a way that, like in a midterm or stuff, it might be, you could have some conceptual questions there, but it's for the most part, I don't think that's going to be something that students would be inclined to think about. Yeah, I like these blueprints. I have them in every chapter. I think they just summarize the chapter. So if you're thinking about pathways, we have path of least resistance and just create a course, create a model, something. Other pathways, if you're thinking about undergrads or grads, or let's say engineers, practitioners, there are multiple things that you could do to learn. You know, it goes really from things that you can learn on your own versus things that you could learn as a community. So summer courses is something that you would do yourself. Electives or existing courses, this is something that you would do yourself. Mocks, the same thing. Social media stuff, seminars and society seminars or conferences, this is something where you would go visit, go for an hour or, like 5 minutes a day scrolling down your favorite app for social media and, figure out stuff from there. Learn a few things about AI, machine learning. We have, of course, questions and problems. We have the solution online too. You can have a look at that. I actually, when I did this the first time, I really wanted to want the faculty members to think about this. So these questions and problems are actually for students in this chapter. I wanted it to go back for the instructor or faculty member, and then put down your thoughts, like what are other things, or how would you modify this, or what are the limitations of these things? How can you make it better? I think that's a good exercise because as you become more faculty and less student, we get to lose that touch with doing homework and stuff. Let's see, I think this is the end. Oh, perfect. So this was the end of this recording. You'll see me soon for recording for chapter 2. As always, if you have any questions, please let me know. Feel free to reach out to me. I'm really hoping these recordings will be something interesting, and I have a feeling this was like about an hour or less than an hour, so that'll be great. Thank you all.